All right, let's start the next chapter. Next chapter is pretty short. We'll be able to get through this one, maybe two videos. Carboxylic acids. Okay, let's look at the basics of carboxylic acids. Of course, we got our carboxy group. This carbon is sp2 hybridized. It's trigonal planar, and it is polar. Negative, partial negative charge on the oxygen, partial positive charge on the carbon. Nomenclature. When you name your carboxylic acids, we often go by the IUPAC, especially for our larger molecules. We tend to stick with IUPAC. It just makes more sense. Again, just like naming things with IUPAC, you look at the longest carbon-carbon chain. The deal is that longest chain must contain the carbon of the carboxylic acid, and the carbonyl carbon here is carbon number 1 in the chain. Carboxylic acid, very important functional group. Its carbon is always carbon number 1. And once you find that longest chain, you just drop the E and add oic acid. For example, if you had this carboxylic acid right here, note our carbonyl carbon is 1, 2, 3, 4, 5, 6. 6 carbons, including the carbonyl carbon. A 6-carbon alkane is hexane. We drop the E off of hexane and add oic acid, it becomes hexanoic acid. All right. Occasionally, you'll find a situation that it's tough to name it that way when you have rings like a cyclohexane ring and our carbonyl carbon is not part of the cyclohexane ring. We name it this way. Here you had a cyclohexane ring. This carbon, the carbon that contains the carboxylic acid, has to be carbon number 1 of our ring. The carbonyl carbon, the carboxylic acid, has a substituent on this ring, makes this carbon number 1. So then this is 2, 3, 4, 5. So this is 2, 5, 5 trimethyl cyclohexane carboxylic acid. Yeah, we just do it that way. If you've got a ring with a carbonyl carboxylic acid hanging off of it, we just name the ring 2,5,5 trimethyl cyclohexane, and then just add carboxylic acid to the end. Sounds fun. Common names. Note there's a table in your book. I'm not sure if this is the right table. It's table 19.1. Not sure about the page. This might be an old edition. You just have the parent name and add ic acid. So CH3, CH2, C double bond O. There are 3 carbons here. The common name has this group right here. CH3, CH2, C double bond O is called the propion group. Propion. And so, since it's a carboxylic acid, it's propionic acid. All right. You need to memorize the first couple in that table. I will write down part of the table here. HC double bond O is called form. That's the form group. CH3, C double bond O is the acid group. CH3, CH2, C double bond O, as we just found, is propion. And CH3, CH2, CH2, C double bond O is the butyr group. BUTYR. I'm not sure. Yeah. Okay. BUTYR. Yep. So note that means if you had CH3, C double bond O, OH, IUPAC says, okay, 2 carbons in the chain would be ethane. You just drop the E and add oic acid. This would be ethanoic acid. Common says, oh, this group here that you can see, this group is the acid group. So you just have acid and you add ic acid, acetic acid, or acetic acid. All right. Last thing, just because it gets a little crazy, uh, and we're going to find out it's going to be very useful. The common way of naming things, that when you have a carbonyl carbon, in general, the thing to the right of it, the carbon to the right, we call it alpha. So when you're talking about alpha carbons and beta carbons, you're starting with the thing next to a carbonyl carbon. So note that this, for IUPAC, this is carbon number 1, and this is carbon number 2. For common, this is carbon alpha. So carbon 2 in IUPAC is alpha carbon in the common name. So here's our carbonyl carbon. The one next to it is alpha, the one next to that is beta, gamma, delta. The last one would be called omega. So if we were naming this molecule, note 1, 2, 3, 4, 4 carbons in our longest chain, including the carbonyl carbon. So if carbonyl carbon is number 1 in IUPAC, we'd call this carbon 1, 2, 3. This would be 3-methylbutanoic acid. But the common name says, oh, here's our carbonyl carbon, here's alpha, beta. This is beta-methylbutric acid. Other common names you need to know, if you've got 2 carboxylic acids and the 2 carbonyls are bonded to each other, that's oxalic acid. If there's a CH2 between the 2 carbonyls, that's malonic acid. If there are 2 CH2s in between the 2 carbonyls instead of just 1, that is succinic acid. So you just kind of have to memorize those guys. All right. And note, when you deprotonate a carboxylic acid to make the salt, you drop ic acid and add 8. Therefore, if you add CH3, CH2, C double bond O, K plus, you just say, okay, what if there was actually a hydrogen on here? This would be propanoic acid. 1, 2, 3, propanoic acid. We just drop the ic acid and add 8, so that would be propanoate. Potassium propanoate. Yeah, write that down. Make sure we got this right. If it was the acid, it would be propanoic acid. We drop ic acid, drop the ic acid and add 8, so that's propanoate, potassium propanoate. Note, if you're using the common name, because that was IUPAC we just did, common name, this group here is the propion group. So this would be potassium propionate. So potassium propanoate or propanoate and potassium propionate are the same thing. And that's a little tongue twister issue right there. All right. Okay, physical properties of carboxylic acids. They're polar, do lots of hydrogen bonding, which means if there's 5 carbons or less, they are water soluble. They tend to have higher boiling points than alcohols because they are more polar. They're soluble in organic solvents. Even acetic acid is soluble in organic solvents. They've spectroscopic properties. Review your IR and the NMR. Recall in the IR, carboxylic acids have very large OH groups, very wide OH groups, tend to have fairly wide peaks, especially the carbonyl peak. NMR, the hydrogen bonded to the oxygen of a carboxylic acid comes around 10 to 12 ppm and is a broad peak. Interesting carboxylic acids, there's a bunch, read about it. How do you make carboxylic acids? Oh, so many ways. We could oxidize primary alcohols. You just take a nice primary alcohol, add a little potassium dichromate, H2SO4 for a catalyst, and some water, and you get the carboxylic acid, chapter 12. We've found this with alkyl benzenes. If you have a benzene ring with a CH or CH2 or CH3 group on it, potassium permanganate makes it a carboxylic acid. One of my favorites, oxidative cleavage of alkynes. I love ozonolysis. Ozonolysis is osmolysis. Okay, you take a internal alkyne, add ozone, a little water, you get 2 carboxylic acids. You basically just split this triple bond. This carbon becomes the carbonyl of one carboxylic acid. This carbon becomes the carbonyl of the other carboxylic acid. Note, with a terminal alkyne, if you've got a hydrogen at the other side of the C, terminal alkyne, this carbon becomes a carbonyl of a carboxylic acid. This carbon becomes carbon dioxide. You get the carboxylic acid and carbon dioxide with ozonolysis. All right. Reactions of carboxylic acid. Well, it's an acid. It will react with base. So a carboxylic acid, such as acetic acid, such as a base hydroxide, this hydroxide will take that hydrogen to make the conjugate base of your carboxylic acid plus water. Note, based on all our fun remembrances of Chapter 2 and pKa tables, we know that the carboxylic acid with a pKa of 4.8 for acetic acid is a stronger acid than the conjugate acid in this reaction, water. All right. It turns out this is going to be a big problem with our carboxylic acids. We're going to like making carboxylic acids. They are stable. They can do many things, but their biggest foible is that you put in a base and it will react as an acid with any base. You put in hydroxide, it'll react, or especially anything stronger than hydroxide, and instead of doing the reaction you want it to do, such as substitution, it will just do an Bronsted acid-base reaction and pull that hydrogen off. And so that is a problem that we're constantly having to sneak around with carboxylic acids. And the reason carboxylic acid likes forming bases so well is because the conjugate base of a carboxylic acid, carboxylate, has resonance forms. Note, if the resonance forms tell us that this molecule is more stable than you'd think. The real resonance hybrid is more stable than either of these two. If you look at the stability of this guy with a double bond and a single bond, you find out the resonance hybrid is more stable than that. This is the product of your acid-base reaction. Therefore, if the product is more stable than you think it is, the reaction goes towards the right more than you think it should, and therefore these are more acidic, pKa of 4 to 5. Because anything that stabilizes the conjugate base means you have a stronger parent acid. The reaction is going to go to the right. So note, the conjugate base of ethanol is not resonance stabilized, pK of 16. Note the conjugate base of phenol, if you take away this hydrogen here, we've got negative charge, but one of these pairs, if can get delocalized into the ring, resonance makes this phenol much more likely to give up this hydrogen because its products can be resonance stabilized. Look at the inductive effects of carboxylic acids. Disubstituted benzoic acids means, okay, if we have a benzene ring that has a carboxylic acid on it, note if you have an electron withdrawing group on there, electron withdrawing groups such as nitros or other carbonyls, they're withdrawing electron density away from the ring. Through inductive effects, withdraw electron density away from the carbonyl, which draws electron density away from this oxygen, which draws away from the hydrogen, making this hydrogen more positive, making it more acidic. Electron withdrawing groups such as nitros and aldehydes and ketones on a benzene ring will make the carboxylic acid part of the benzene ring more acidic. Electron donating groups like nitrogen, anilines, OH, methyl groups. Electron donating groups make it less acidic because they're donating electron density to the ring, so the ring has more to share. This hydrogen is not as positive through inductive effect, less likely to be given off, less acidic. Okay. So, that's the reaction of carboxylic acids as acids. It turns out, however, we can actually react carboxylic acids with other acids if you have a very strong acid, such as sulfuric acid. because we've got two oxygens here with lone pairs that might attack the acid, and there are two ways the reaction could possibly happen. A lone pair on the carbonyl oxygen attacks the hydrogen of the acid, kicking off A minus, or the lone pair on the oxygen of the OH of the hydroxyl group attacks the hydrogen, kicking off A minus. The question is, which way will it go? Hint, usually goes top way. But let's look. If the carbonyl oxygen attacks the hydrogen, we get this molecule right here with this hydrogen on this oxygen and positively charged. If the OH, the hydroxyl oxygen attacks the hydrogen, we get this positively charged oxygen with H2. Either way, we get a positively charged oxygen, which isn't the happiest of beasts, as oxygen is electronegative and does not want to carry positive charge. However, note this carbon, if we go down this way, has oxygen and hydrogen. Up this way, oxygen and hydrogen. The only difference is the bonding, the electrons, which means this has resonance forms. We can move the pi bond up here to make those two have positive charge on this carbon, or then move these electrons here to have it down here. We are delocalizing the positive charge when we make this guy. Resonance stabilized. No resonance forms here. You can't make resonance forms. You can't have these two electrons go here because then the carbon, it's just not going to work. We don't have the possibility of resonance forms with this guy. Therefore, since this route gives us a more stable product, most of the time when carbonyl groups, especially carboxylic acids, find a strong acid such as H2SO4, it is the carbonyl oxygen that gets protonated most of the time. All right. The next thing we're going to look at is nucleophilic attack, and although we drew it this way, this is actually very difficult to do with carboxylic acids. If you want a nucleophile to attack this carbon, now one would say, but wait a minute, oxygen's electronegative, carbon is positive, less electronegative, so we've got a partial positive charge on this carbon. Won't a nucleophile want to attack this partial positive charge? Well, the answer is yes, it does. The problem is, though, if you have a strong nucleophile, recall that nucleophilicity parallels basicity, which is just a fancy schmancy way of saying strong bases are also strong nucleophiles. In general, strong nucleophiles are strong bases. If we're talking a nucleophile, means we want it to be a Lewis base and attack the carbon. A Bronsted base will attack hydrogens. Strong nucleophiles are strong Lewis bases and strong Bronsted bases, and it's much easier to attack this hydrogen. So this reaction, as written, is actually very difficult to come by. Finding a nucleophile, a decent base, that's going to attack this carbon and not attack this hydrogen, I don't know. That's rough. But we will look more at this in future chapters. All right, we're going to cruise through this. Extraction, recall from good old Organic 1 that if you had, say, a mixture of hexane and benzoic acid, and 7 carbons, it'll dissolve in hexane. How do you separate the two? Well, you add sodium hydroxide, because note, sodium hydroxide will react with this to make sodium benzoate, which is an ionic compound, and now it is water soluble. So good old extraction, the experiment we did in Organic 1, where we had a organic molecule and an acid impurity, and we added base, which made the carboxylate, the conjugate base of benzoic acid, benzoate, which is now water soluble because it is ionic. All right, we're just going to cruise. We're going to finish up this chapter. Video is a little longer than I like, but I am sure you have found it so fascinating that you're not in danger of falling asleep whatsoever. All right, sulfonic acids, something to know about them, that if you have an R group, a sulfur, double bond to one oxygen, double bond to a second oxygen, OH, pK about 7, recall paratoluene sulfonic acid. Oh, remember good old Organic 1, where you had this guy here, CH3, bonded to a benzene ring, bonded to a sulfur, double bond oxygen, OH, and we call this TSOH, and it was, recall, paratoluene sulfonic acid. Now that you know how to name compounds, you can say, oh, well, duh, of course. Toluene, paratoluene, sulfonic acid. Okay. Paratoluene sulfonic acid can be used in place of sulfuric acid. They both have pKs about -7, and both of them have their conjugate base as non-nucleophilic. Last thing we'll talk about is amino acids, something you should know. Because you're made up of amino acids building blocks of protein. Note an amino acid has two functional groups, the amino functional group and the carboxylic acid functional group. And the carbonyl carbon and the nitrogen are connected via one carbon. So you got carbonyl carbon, the alpha carbon, and then the nitrogen of the amino group in your amino acids. All our amino acids have a hydrogen on that alpha carbon and a side chain. And if our R here is an H, it's glycine, and it is not a chiral carbon. But note, if R is anything other than hydrogen, this is a chiral carbon. And you have DNL isomers. Something to realize, all natural amino acids, every amino acid in your body, other than glycine, every amino acid in your body is the L isomer. Every amino acid in your body rotates plane polarized light to the left. Another way of saying it is life rotates left-handed. Okay. Also note that the amino acids cannot exist in this form at neutral pHs. In your body, if you're in your bloodstream, in your cells, the pH tends to be fairly neutral, close to 7, while acids deprotonate at pHs of 7. Bases protonate at pH of 7. So at pH 7, in neutral solution, the carboxylic acid end is deprotonated to the carboxylate. The amine end is protonated to the ammonium, and you've got a positive nitrogen, alpha carbon, carboxylate group here, and this is called a Zwitter ion. All right. So that is it for this chapter. Nice short chapter here. We will continue next time. We are going to go to carbonyls. Look at some interesting stuff about carbonyls.